Today, let's take a look at doing some coaster energy calculations. Your mission, which you must accept, you can do it right in the packet or in your notebook here, is we're going to try to find the speed of the roller coaster at any point along the ride here. So I'm going to break it down all from scratch to help you see how this works here. The very first thing I do is picture what the energy is involved in your coaster. So this is, rather than me trying to draw a roller coaster, which is scary, this is the Viper. I don't know if you've ever been on that, in the Southwest Territory by the Raging Bull. Fun ride. It's a classic. It's a wooden coaster. I usually don't like wood because I feel like I'm going to die. Like on the Eagle, it's like all rickety and there's that little stupid bar that holds you in. I'm talking about. But the Viper, I'll go on because it winds through. It's like an Indiana Jones kind of feel through the mine. Classic coaster right here. Real simple. The coaster always starts somewhere. So let's sketch it out. In this case, on the sample problem, it starts at point A. The height of point A is how tall? It's given how high? 120 meters above the ground. And really easily, you can tell which ride's going to be the fastest by just looking for which one's the tallest. Six Flags, which one is the tallest? Anyone know? Yeah, Raging Bull. So when you're at the top of the Raging Bull, just look around. It's a nice view of the whole park. This is at point A. And what's the speed at point A? The initial velocity is given as how fast? 2.1 meters per second. Yeah, don't get visually overloaded by all the info. Just break it all down. VI. And usually you're not moving very fast on the first hill because there's a machine traditionally called the chain dog. And you know when you're going up the hill, it goes chunk, 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 chunk. You know what I'm talking about? That's the chain dog pulling you up. It's a pulley, motor-driven machine that does work to lift the coaster carts against gravity to store up your potential energy. Then you go down the hill, and using common sense, when you're down the hill, are you going faster or slower? Obviously. Obviously, you're going to be going what? Faster. You don't even have to take physics. But the trick is not you're going faster, but exactly how fast are you going. To know that when you design a coaster, because then you can figure out the forces on the person's body so you don't kill anybody. Our next unit, we're going to look at G forces. That's an important idea. Most people, you can't take more than like 6 Gs, 6 times the force of gravity, because then you start to pass out, get headaches, that kind of thing, whiplash. So point B, we want to figure out how fast you're going. What's another way to say how fast you're going? V, F. Half the problem is knowing what the problem is. So the point is we want to figure out what's your final speed, what's your velocity final at each point along the ride. So the hardest part isn't really the math, it's breaking down all the information. In real life, you may or may not go on to be a roller coaster designer in real life. That might be a fun job. But will you ever have to solve complicated problems, break down information, think logically, systematically, and solve problems with a guided process? Of course, and that's what we're trying to learn. So in step 2, the secret, when you break down your knowns and unknowns, is to separate information into 2 columns, not X and Y for projectiles, but what for energy? Anybody know? Energy initial and what? Energy final. In other words, you're trying to picture in your head what kind of energy did we put into our pie, right, at the start, and then at the end, how did that pie get divvied up? Because what you start with is what you end up with. That's a big idea, conservation of energy. The total energy in any system has to stay constant. So at the very start, what kind of energy do we have in our roller coaster? Is it moving? It's moving a little bit, right? 2.1 meters per second. What do you call that when you move? Kinetic. There's a little bit of kinetic energy. But I heard it. What are we storing up big time? What's the whole point of lifting it really high? Potential energy. That's correct. PE initial. At the very end, is it moving? Oh yeah, big time. It's moving a lot faster because it's going down that big hill. And does it have potential energy? Of course it does. It's still 60 meters above the ground. All you're doing is you're converting PE and KE to PE and KE at the end. It's just in this case, we're mostly converting potential energy into kinetic. You know what? It's kind of like that accounting class. Anyone taking that in business upstairs? Except instead of dollars and cents, we're counting joules of energy for kinetic and potential. So kind of like you have to do your taxes by April 15th or you go to jail. Make sure you get that in. This is accounting, but for nature. Energy's got to come somewhere. It's got to go somewhere. Next, let's break it down. How do you find KE? 1/2 mv squared, correct. So we need to know mass, and we need to know velocity. In this case, the mass is given. What's the mass? For all problems, mass is equal to 2,500 kilograms. At the end, should the mass change? Hopefully not, unless somebody falls out of the coaster, they lose a flip-flop. That usually happens every so often. We have one student on the field trip, they lose their flip-flops. So kick them off, or that day wear sandals, right? Initial velocity. What's initial velocity? given in the problem, 2.1 meters per second. What's the final velocity? Oh, wait a second. That's what we're trying to find, right? That's the whole point. So for VF, put a box around it, star it. Don't lose sight of the goal. Don't get lost in the forest for the trees there, right? Always have a big picture view of what's going on. We're trying to figure out exactly how fast is that coaster going at any point on the ride. Got it? How do you find PE? mg what? How do you find PE? mg everybody. So we need to find the height in each case. And gravity. What's gravity on Earth? I forgot. Welcome, we come in peace, right? Gravity is what? Does gravity change? We come in peace. Gravity is 8 meters per second squared. Someone might say, wait a second, Mr. Lau, I always thought it was negative 9.8 meters per second squared. Okay, the negative is when we did free fall. To remind us that gravity accelerates you which way? Down. Energy is not a vector. It doesn't have direction. It's just a scalar. And since we're only looking at potential energy against gravity, energy is a positive number. We don't put in a negative in this case. So here, you don't want to memorize blindly. You want to apply the mathematics intelligently to try to understand what happened. Height. What's the initial height? 20 meters. And the final height is 60 meters. In other words, we're converting 50% of the potential energy into kinetic. That's really what's going on. See that? The big picture. Step 3, tie it all together. What's step 3? You write out the equation that relates the what? The knowns to what? Unknowns. So wait a second. I don't have an equation that just has the F all by itself, right? And that's because the big idea equation, the big idea is whatever energy we start with is the energy that we end up with for any system, the conservation of energy.